specific type of materials at least. And then we'll talk about applied nanostructures and device materials. So this is essential because when you think about materials processing, and then finally implement it in a device, then the device operation does depend upon the materials processing that you adopt. Now, I believe Sona College is not very far from here. So you're all welcome to this very beautiful campus I inhabit. So now that there is lockdown, animals are happier. So if you come at this time, you will actually enjoy their playfulness and the scenic beauty of campus even more. Okay. So with that, I proceed. I'm having some issues with changing slides, so I'll probably have to do this back and forth. Okay. So a bit about where I am from. So I'm from IIT Madras. Sorry for this. It's gotten chopped off a little. And to make this presentation relevant to all of you, I wanted to just tell you that some of the activities that I do is directly relevant to chemists, physicists, materials engineers, chemists, chemical engineers, applied physicists, electrical engineers, and I have all of them in my group today. And I've been very lucky that way because I've been able to somehow learn from people coming from each of these backgrounds, and that has been an enormous joy. So, for example, one of the chemistry students, he was very involved in water splitting technologies, and he came up with an approach using which mercury contaminated water, and there are parts of the country wherein there's a lot of mercury contamination. So he started using that mercury contaminated water and developed his own hydrogen production, hydrogen generation, water splitting technology. And it has been a very interesting development, and a lot of engineers have jumped on that result after that. There are experiments ongoing wherein people are thinking about using that generator, coupling it with an IC engine, and so on and so on. So very exciting things. So it started from chemistry, now it's landing in mechanical engineering. So it's very enjoyable to see such a trajectory. The next one is BSA complex. So some of you again might be from applied physics or physics related backgrounds. You must have studied spectroscopy, even chemists study spectroscopy. Here is a spectroscopic approach using which we were able to make a technology, very handheld, very simple technology, using which at the point of use, you would be able to determine heavy and transition metal sensing. With one of my colleagues, Professor Sriram Kalapati, who is a polymers expert, I continue to work in this area today. And it's an area that is somewhat close to my heart because it seems to be necessary in a society like ours to be able to come up with handheld, simple solutions that are also foolproof, especially when it comes to mitigation of pollution and such grand challenges. Next is spectral tuning methods using one-part chemical approaches for ternary oxides. So let me simplify this a little bit. So spectral tuning means modifying the spectra. It could be luminescence spectra in particular. And so modifying that by using one-part chemical approaches. What do I mean by that? What I mean by that is, suppose I make a reactor. I don't need to have a multiple set of reactors in tandem in order to modify these materials. I could in principle do it in one shot. Okay? And that would be very interesting from an industrial standpoint, because then immediately the technology would become industrially relevant because you don't need as many processes. So the process flow simplifies. So here is an example of a category of problems wherein you are driven by engineering thinking, but the solutions come from physics and chemistry. Okay, so that is very interesting, isn't it? So I again hope that in my lifetime, at least, I see our colleges opening up to interdisciplinary education and learning and so on, and also hiring. In fact, that would be good for everybody because you can see the benefits of such thinking. You know, it comes from, let us say, an applied orientation, but you cannot solve the problem without deep science. Okay, and then we have also been making our own high pressure reactor facilities. And you can see here there is a stronger interface with something like chemical engineering. So you will have chemistry inputs, but the solution comes from chemical engineering or materials engineering and so on. So there is this constant crosstalk of disciplines, which I think should happen in all our colleges and institutions. And I hope to see that over the next few years. Many of you are teachers, I'm told. So it might be a nice thing to sort of contemplate. You know, what does it mean to enter into a richer world wherein we seamlessly talk to one another, scholars to scholars, researchers to researchers, and so on. Next is size focusing of ultra small particles This is again something very, very cute. I mean, we ran into this entirely by accident, and I find it very fascinating. Typically, what happens is, and chemists here would know this, if you have a bunch of different sized particles, small particles and large particles, and you heat them up, then the larger particles would basically grow at the expense of smaller particles. By that, what I mean is small particles would get smaller and smaller, and the large particles would become bigger and bigger. And the argument for that comes from thermodynamics. So it comes from the surface chemical potential of atoms sitting on top of particles. So if I have a particle like this versus a particle that is like a football, then the football on the surface has lesser curvature. And as a consequence, an atom sitting on top of that is less energetic than an atom sitting on top of, let us say, a tennis ball. Okay? I mean, these are crude analogies where the tennis ball and large football basically are analogous to a small particle and a larger particle. So what we found is that you can actually have a technology wherein the small particles become larger and the large particles become smaller until they freeze around or basically converge around a certain critical radius. That is very exciting. And we were among the first few to sort of discuss this thermodynamically. And now we have elucidated a set of thermodynamic rules using which you can design this process. So that is also quite fascinating. So competencies, so there is some chemistry competency, including air sensitive chemistries and things like that. But we also do quite a lot of crystal growth, particularly nano crystals, increasingly so, and low dimensional materials. And this being a group that has a mix of both engineers and scientists, we actually do a lot of experiments, but we also do a lot of simulations. An increasing number of simulations which uses artificial intelligence and machine learning for doing materials design. Okay. So to make this talk somewhat accessible to all of you and maybe even relatable, because I'm also told that there are BSc students here, and all of you, please feel free to unmute yourself and ask a question in between if you wish. But I will try to pause in between, and I'll try not to go overboard. I'll try to stop sufficiently early so that we can have one-on-one conversations even. That would be very nice. That way, whatever is being presented wouldn't be just something that is misty and lost in cloud, but it would become something that is meaningful for you. Okay. So let me start by asking this very basic question. And some of you are probably already taking some courses to do with electrical properties of materials, physical properties of materials, even chemical properties or electrochemical properties of materials, and so on. So I'm going to sort of zoom out a little bit and ask this question: why bother about electronic properties anyways? So the broadest definition of electronic properties is basically the behavior of the material, both steady state as well as dynamic, which draws from the electronic structure of the material. So what do I mean by electronic structure of the material? So all of you in your high school would have studied about chemical bonds, and chemical bonds are easier said than done, in the sense that they are harder to understand because you can ask very basic questions about them, and you will start realizing that the nature of chemical bond is somewhat deep, because it ultimately comes about, if you think about it, because of the delocalization principle, because of the Heisenberg's uncertainty, because electrons that are in the vicinity of two different nuclei basically get delocalized between the two different nuclear centers, and hence the bond comes about. Now you can ask questions about the nature of these electrons in materials and ask questions about how these electronic behavior, for example, this electronic behavior could get modified when you perturb the system. By perturb the system, what I mean is, suppose I tap it, dance on top of it, okay, yell at it, take a hammer, hit it. How is it going to actually impact the material and hence the electronic structure? One of the great successes of physics and chemistry of solids in the last 50 years has been the realization that all properties of materials, absolutely everything, mechanical, electrochemical, chemical, physical, everything, anything you can think about, physical and chemical, are described by using electronic structure. Okay, so once you know the electronic structure of the electrons, that means you know where the electrons sit in energy space. you by and large know the behavior of the material in its entirety. You know the electrochemistry, you know the chemistry, you know the physics, you know all the rest of the properties associated with the materials. And that is arguably one very fundamental reason from a physics standpoint to learn electronic structure of materials and to appreciate electronic properties, because they are not independent of things like mechanical behavior or electrochemical behavior and so on. But you could put on an engineer's hat and then also think about utility of such behavior. For instance, I can think about a bimorph system. A bimorph system, bi means two, morph means structure or block. This is basically the root for the word morphology. For instance, morph stands for body, unit, etc. So two units. So here I have a piezo 1, piezo 2, and one on top of the other. And if I deform it in some manner, then lo and behold, there's a voltage reading that you get from it. So it behaves as if it's a battery. Okay, so it is a mechanically actuated battery. When I have two such piezos, one on top of another, I can have even a single piezo, no problem, and I would get a voltage reading. It will not be nearly as high as if I had a bimorph. And this has been used, by the way, in blind sticks. People who are not sighted, they use blind sticks. They actually use the uh, bimorph cantilever. And when they tap on surfaces, the degree of the deformation tells them how hard the surface that they're tapping on is. Now, here is something that I think some of you who are chemists might actually find interesting, maybe even those of you who are physicists. So this is taken from one of those reports wherein people are reporting essentially atomic scale, molecular scale transistors. So I basically have a cone of gold atoms and another cone of gold atoms, and they are both linked to one another essentially by an atom. In practice, it would be across few atoms. But what do you know about atoms? Well, what we know about atoms is that their energy levels are quantized. And when their energy levels are quantized, that means to say if I draw current from left to right by applying a potential, then I would also get currents that are quantized. Now, that is wonderful. And it is a phenomenon called Coulomb blockade. And it can be widely used for making switches. Just think about it, the switches in your houses, in your college, and so on. They are on-off switches. But what if you had a system wherein I have off, on 1, on 2, on 3, on 4, on 5, on 6? Suddenly I have a switch that encodes a lot more information. And such systems, because it can encode a lot more information, and arguably they also open up to quantum mechanical states. You can engineer quantum mechanical states. You could use it for things like quantum computation and so on. So what determines electronic properties any which ways? So this is something that I think both chemists and physicists here might connect to, because many of you have studied the Huckel theory in your quantum chemistry or quantum mechanics course, or in your solid state physics courses. Basically, it is a model by which you can use atomic orbitals in order to construct crystal orbitals, right? So for instance, if I have silicon crystal, then I know the orbitals associated with silicon atom, and by extension, I would be able to construct the crystal orbitals. Okay, so the bands as a consequence become a function of the bonds of the material. And once I do that, that means to say that in order to do that, I need to write a Hamiltonian, and the Hamiltonian has a V of R term, which is the potential term, and that potential term depends upon things like periodicity and so on. So once I have the kinetic energy term in the Schrodinger's Hamiltonian, and I have the potential energy term, I can actually solve it as an eigenvalue problem. And then lo and behold, I have the energies associated with the material, with the electrons in a material. It is easiest if it is a single atom or if it's a periodic cell. It is difficult if it is something like a polymer, because you can still use this model, but the V of R is complicated. You have to have multiple numerical terms in your V of R. So you can start with the Hamiltonian, you can solve for it, and then the theory can inform your experiment. And this cycle between theory and experiment is where a lot of innovation possibilities arise. So you can start imputing things. For example, you can start deducing things. You can say, if I add more silicon atoms into this particular alloy, this is likely to happen. That's good for us, etc., etc. So a good fraction of today's theory and modeling goes into being able to connect experiment to theory. Okay. Now we'll turn to energy, because Sona College is clearly running a program on energy today. So it's a good idea to look at energy. And in the context of energy, let me just use a microphone. It might sound better. Sridharan sir, are you able to hear me?
Yes, sir, very clearly.
Very
No issues.
clearly. Okay, so I'll use
Yes.
this. This is better, perhaps.
Yeah,
Okay,
okay.
so we'll look at the lighting segment, and the reason why I'm talking about the lighting segment is because something like 24% of, on an average, of a city's energy expenditure is into lighting, goes into lighting. And if you look at conventional lighting, which is bulbs, it is only 2% efficient, by the way. That means for nearly 100 watts that you give in, you get 2 watts worth of light. You can see that conventional lighting sector is shrinking as a function of time. It's shrinking dramatically, and it's expected to basically go out of vogue. Other than for purely aesthetic purposes, architectural purposes, you might anticipate that the old style incandescent bulbs will basically phase out. Now, LED lighting, on the other hand, is having a super exponential growth for a long time now. Okay? So we'll look at materials associated with LEDs, and why should we care about it in an energy conference? Well, we should care about it, or in an energy workshop rather, because of the fact that LEDs, the world's best LEDs, are about 81% efficient. The theoretical efficiency of an LED can be 100%. The world's best is, as I said, in the vicinity of 80%. And the ones that you find in the market are 40% efficient. The incandescent bulbs, on the other hand, are 2% efficient. So if you want to head towards energy efficient economy, having LEDs and ability to manufacture LEDs is essential. It will become bread and butter. But let us look at the situation right now around the world. You will find that there are very few parts of the world where LEDs are actually manufactured. All the rest of the places are assembling, they are not manufacturing. So there's a lot of value to having the capacity to make these on our own. Okay? So in that context, we started looking into novel phosphors. Phosphors are materials that are light emitting, and that means to say you could excite it by using either an electrical excitation or basically by applying optical excitation and so on, so that you could get the light of your choice. And these materials find application in things like LCDs, LEDs, VFDs. So LCD is a liquid crystal display, and many of you probably all have experience with liquid crystal display devices. LEDs I have already mentioned, light emitting devices. VFDs stand for vacuum field devices, so they are very widely used in display screen technologies. Then field emission devices, FEDs, X-ray screen detectors, and so on and so on. So now let's look at a device. Okay, so you have the phosphor layer. You can see it is drawn in purple, and it is sandwiched between two gray layers, and the gray layers are insulating materials. And on top of that, I have the electrode. So what am I applying? I am applying a potential gradient across this device structure. Current goes through it, very often through tunneling. So these are very tiny, thin structures. And those of you who are doing an MSc might actually have solved tunneling problems. Maybe in Tamil Nadu, even the BSc students solve tunneling problems. So these are quantum mechanical tunneling problems where a particle can enter a region which is classically forbidden. Okay? And so you can actually have a tunneling based device, and then you could excite it. You could also excite it by using UV and get visible light. So there are other structures possible for this device. And the engineering parameters you should care about are things like conversion efficiency, chemical stability, thermal quenching, which means to say at device operating temperature, it should not lose its light emitting capacity. Then thermal stability, that means to say that when you heat it, it should not basically become another material. It should not undergo a phase transformation, particle size distribution, and so on. Now, let's look at this. Actually, let me
explain this because this audience would understand this. Let me, I'll, all right. So before we go into some of this, which you might have seen in your textbooks, the applications for these kind of materials and the devices thereof are in a wide range of civil sector, so telecom, for example, but a lot of military sectors also. So the red color applications are all military applications. The other one are commercial and civil. For example, ship radar, airborne radar, shipboard radar, etc., are military applications, and these are the civil applications. And you can see that these type of materials do find applications in a wide range of devices. Now here is a unit cell. Those of you who are students, you might have actually learnt of the 7 crystal systems, and as part of the 7 crystal systems, you were also taught about the unit cell, and you were taught about the Bravai lattices and so on. So this is basically something called as a Woodside cell. A Woodside cell is something that has what is called as a zinc blend structure. So one of the naturally occurring ores of zinc is zinc sulfide. So zinc blend stands for that. And its crystal structure, keep the crystal structure as is, knock the zinc off and put gallium there, knock the sulfur off and put nitrogen there, and you will get gallium nitride. So it is called Woodside crystal structure. And among the crystal systems, it belongs to the hexagonal crystal system. Now what I'll do is I'll knock out one of the gallium atoms and put europium inside them. So I have plenty of gallium atoms in this crystal, but I knock out some of them and put europium in them. So in which case it is called doping. And when europium dopes at the gallium site, it becomes europium 3+, and the emission associated with europium 3+ can be depicted as follows. So I have some term symbols here. I don't know if the undergrad students, the BSc students would know about term symbols, but MSc students who might have taken a spectroscopy course might know, faculty would know, especially if you're teaching the spectroscopy course. So this is written just like the molecular term symbols. Okay. So the 2s+1, capital L, subscript capital J notation. Now these term symbols designate the various energy levels, and then you can see that there can be excitation and then there is relaxation. These downward arrows are relaxation events where the electron from here comes to this energy level and out comes a photon of this wavelength. This is just Planck's law in action because I have E2 minus E1 is equals to some h cross omega. All right. And what happens from the point of view of the material? Well, I have the luminophore. Luminophore is basically a light emitting atom surrounded by ligands, and all of you might have heard the word ligand. So in this particular case, suppose I knock this gallium atom out and I put europium, and this europium atom is surrounded by nitrogen atoms. So nitrogen atom would be considered a ligand. I could excite it, then this complex between the luminophore and the ligands could actually change its configuration. There could be a real physical change in the interatomic distance. And then I would have some relaxation events and then finally emission event. Now notice that the absorption and emission are offset by a certain amount of energy. For example, you can clearly see that this energy will be higher than this energy. So the energy for excitation is higher than the energy associated with the photon that has been emitted. Now, so what? Well, that clearly means to say that there is a shift. There is a red shift. And those of you who are chemists, you call it hypsochromic shift. More generally, this luminophore based shift is called the Stokes shift or Stokes loss. Now, those of you who teach spectroscopy in Raman spectra have used this idea of Stokes shift and anti-Stokes shift. This is a generic word used in the context of luminescence spectroscopy. So you have a Stokes loss, and it turns out that the Stokes loss is a function of this bond strength. Okay, so the tighter the bond, for example, the lesser is the Stokes shift. So the closer will be the energy difference between the absorbed photon and the emitted photon. All right. Now let us look at a slightly practical question. How do I make this kind of material? I told you that you can move out some zinc atoms, put some gallium atoms, move out sulfur, put in some nitrogen, etc., etc., and then some of those gallium atoms you replace it with europium. How do you do it practically? It turns out it is not that straightforward. So you can start with something like gallium. For the moment, you can forget the word alloy. I'll come back to it right in a while. And I can nitride it. That means I can flow ammonia at very high temperatures, and then gallium would react with nitrogen. On the surface, I would have gallium nitride. But what would happen is gallium nitride would form a crust, and the remaining part of gallium would remain unreacted. So you have very small, very tiny conversion of gallium to gallium nitride. That's a serious problem. So what we found is that if you make a alloy of gallium and bismuth, and the argument comes from phase diagrams, and phase diagrams are things that all of you might have encountered at some point. I think most BSc students are taught some bit of phase diagrams, the Gibbs phase rule, binary phase diagrams in particular, I think you are taught to read. And even physicists learn this. And phase diagrams are extensively seen in condensed matter systems, for instance. And yeah, somebody wanted to talk. Okay, so you can use this kind of a system designed using phase diagram. So it turns out it's a gallium bismuth system, and you can add a tiny bit of europium also into the alloy. You have to homogenize the alloy and flow ammonia through it throughout for a few hours, and lo and behold, you get europium doped gallium nitride with an emission at 620, which is red color, by the way, okay, which is red color. So this is how we made a device out of it. So we did electrophoretic deposition. What is electrophoretic deposition? I think some of you who would have taken a chapter or two of colloids would have taught or learned about electrophoresis. So milk is a colloid, blood is a colloid, most soap solutions are colloids. So not all soap solutions, but most soap solutions are colloids. So what is electrophoresis? So you have these colloidal particles that are bouncing around in the dispersion medium, and I can apply an electric field, and the colloid basically moves either in the direction of the electric field or opposite to the direction of the electric field based on whether it is positively or negatively charged. So here, using these particles of nitride that were pounded together, that was ball milled and as a consequence made very, very tiny, they were dispersed in this bath. So you were able to disperse them, and you have to stabilize it, make a stable colloid, something like milk. If your milk is rendered unstable, you squeeze lemon inside your milk, it becomes curdled, right? It's exactly the same. So, and if it is curdled, you can't use it for making tea. It's something analogous here. So the colloid has to be stabilized so that you can use it for electrophoresis. Okay? So you have stabilized it, use it for electrophoresis, you get these very nice deposits, and then the device structure I showed you is what was realized, and this fantastic red emission is observed. And those of you who are interested in mechanisms of things, more scientifically inclined, you will realize that, if I change pressure and temperature as thermodynamic variables, I would be able to see the luminescence intensity variation as a function of pressure and temperature, and that would tell me something about the energy migration happening in the material. So we published a few papers to that effect by studying the energy migration. But we continue to explore new materials that are red light emitting. So here is a material that converts blue efficiently to red, and we have a patent on this. And it's very interesting because it turns out that this material uses europium. You could do the same thing with something like erbium, and you would get a blue to green conversion. What would you have if you have blue, red, and green together? The answer is white. And that is our pathway to making a white light emitting device. And as part of that area in general, there are certain parameters called correlated color temperature, which is basically a correlation with the black body, the Planck black body, and then the color rendering index, which is basically asking the following question. I use this light versus sunlight. How similar or dissimilar are they to the human eye? Okay. So there are very interesting ways to actually measure this and calculate it also just by using the spectra. So we have been over the last few years developing new light emitting materials, And we have been going through the full rainbow from the green to the blue to the red, and also exploring new ways of making white and so on. So this is one of the long-standing areas we have been publishing in. In fact, the a student who will graduate very soon with his PhD, he did some spectacular work on this material, sodium bismuth titanate, and he has demonstrated that sodium bismuth titanate is a very promising lattice for phosphors. So you can actually put certain luminophores and excite these materials. And not only that, what is interesting is that which came out in this paper, wherein using electric field, we were able to overcome some of the optical losses that come about otherwise due to crystal defects. So there is some kind of a compensation that you can actually work with. And in 2015, when we reported this, at that time, the editor was very satisfied with the story because it was a little unconventional a story. Being able to spectrally tune using electric fields is known. There is electrochromism. But here is a case wherein you are actually you're tuning it not directly through some rearrangement of atoms, but through some compensation that is occurring, and you're overcoming chemical disorder related luminescence quenching. That means loss of luminescence. So that makes it very, very fascinating. We'll move to another energy device, namely solar cell. So this is how a solar cell made in, let us say, an organic electronics lab looks like. This is not how a solar cell that is made in industry looks like, but all solar cells would have a p-type material, n-type material, one on top of another, and then they would have some current collectors on top of that, and then electrodes. So here we decided to use zinc oxide as the collector material, so because it's like a sponge for electrons. And on the other hand, we decided to use molybdenum oxide because it's like a sponge for holes. And those of you who are science students, you would have studied electrons and holes somewhere in the context of semiconductors. One way to think about it is to think about it as a donor acceptor, because it's a chemical way of thinking about it, but a very nice, it helps you develop a nice intuition. So suppose I have a material A, and that material A or an atom A gives its electron to atom B due to some reason. Let's say you have excited A, and as a consequence, it gives that electron away to B, or you have excited the EAB complex, as a consequence of which A has basically given this electron away to B. So what is happening electronically is that is a quantum mechanical state of higher energy. Okay? And in that quantum mechanical state, there is a charge separation. There's a separation between the electronic center versus the center of positive charges and the center of negative charges. So you can think of it as a dipole. I hope I'm being clear here. So if I have A and B connected to one another, and then I shine some light, and then I have basically a charge, an electron that basically gets shifted towards one side, primarily because it is a higher energy state. But that means to say that some kind of a dipole has been generated, right? So that is a little bit like the electron hole pair that is created. So you are exciting the material, and in the process, you are creating a separation between the electronic center and the center of positive charges. So you have separated them out. And you can keep doing this by shining more and more light and shining more and more photons. But that means now you have a separation in the centers, right? So you can split them, but it's hard to split them because they are electrostatically interacting with one another. But if you have a sponge here through which this positive charge can basically go down its energy hill, and the electron can go down its energy hill, then I have achieved electron hole pair separation, in which case I have gotten light to give me electricity, because electron going in one direction, hole going in the other direction is electricity, right? Because I can complete the circuit and I would get photoelectricity. So that is the basic idea behind the solar cell, by the way. So I could start with zinc oxide nanorods grown by and large at room temperature, and I could have some A, B kind structures on top of it, and then I could build this structure. And the remarkable thing was we grew the zinc oxide at 85 degrees. That means at very low temperature, the kind of temperatures that all of you can afford to have even in your kitchens, in your own undergraduate laboratories. And and so on and so on. And it turns out that it gave a fairly nice was best by research, because it's a proof that using very low embodied energy, very low energy investment, you can still get some decent solar cells. Okay, so right now we are thinking about other very low cost, very eco-friendly ways of achieving this kind of structures. Now there are other activities, battery materials, hydrogen generation, storage, etc., that happens on this campus, and I'm happy to talk to you about any of these. So you can maybe take a screenshot of this so that you get a sense of what is happening on this campus. And in one way or the other, I get involved in some of such activities or related activities, not all the activities, but something that is by and large cognate to these topics. And you will find colleagues working in these areas, not just here, but also in the neighboring Anna University, CLRI, etc. There are colleagues who work in these areas. Now, environmental remediation and nanomaterials. So the reason why I wanted to put this in was because of the fact that I wanted to tell you that these materials that can be made by using very low temperature approaches are also very good from the point of view of environmental remediation. This is interesting because here you are trying to develop a technology, and that technology was developed for the purpose of an energy device, but you don't have to necessarily use it only for an energy device. You can think about using it for water remediation also. So by the way, this is a concept paper that was written that I'm fond of, to her heart than others. So this one went into chemical engineering science, and I like this because it was a concept paper. It was one of those papers wherein I interviewed industry experts and also water treatment plant managers, and try to understand what their biggest challenges are, and also try to map it to the Indian water policy and so on. So it has been somewhat helpful because later on, at least one United Nations document cited it. So it's nice to know that you're doing something good for the world. Otherwise, I mean, the truth being told that most of us academics, we do things that very few people read. So this is very nice that it found some good use somewhere in an important forum. So that's quite nice. By the way, I was telling you about making materials using low temperature approach. So one of the things that we did was use this reaction. It's a very simple reaction. Those of you who are chemists, you will immediately identify this as metathesis. So metathesis would be something like AB plus CD giving AD plus BC. So you basically have, shuffling of atoms. So it is a metathesis process that was used for making zinc oxide, and this was nano zinc oxide. It was doped with copper, and you see this tremendous improvement in the solar spectrum absorption from 0.4 to 61%, very dramatic. And it's also wonderful from the point of view of water treatment. There is a process called photocatalysis, so you can shine light in media which has this semiconductor, zinc oxide or copper doped semiconductor, copper doped zinc oxide. So you disperse it in water, you shine light, the zinc oxide basically absorbs that some part of the photons. Electrons and holes are created. Electrons contribute to the reduction reaction, holes contribute to an oxidation reaction, and in the process you get organic pollutants in particular cleaned up from water. So we looked into the science of it, and we demonstrated that it's an example of what is called as a type 2 semiconductor junction. I won't get into the details here. Thereafter, I have also been looking at, adsorption, and you will find that these equations come from both kinetics and thermodynamics. So this is sort of describing the adsorption regime. And those of you who even look at biophysics, biochemistry, you would have used these kind of models, something that is somewhat related, because you have a substrate and then you have some stiction coefficient, let us say, the possibility of stiction. And the question is, what fraction of the substrate would be covered? Can you reuse the substrate, etc., etc.? So in response to those questions, you can actually think about the kinetics and thermodynamics of adsorption, which was used in order to understand this multi-phase adsorbent bed that was made in our lab, wherein we combined zinc oxide, copper doped zinc oxide, cobalt ferrite, etc., etc. And this work actually has picked up some traction even in the industry. So now we'll turn our attention to slightly more contemporary areas, and you will find that there is a connection to energy again. So nanorod to dot conversion, and as I said, there is this very cute result we found wherein we were able to see particle size focusing. So before the process that we undertook, there was a very large particle size distribution. Well, large not by chemistry standards or material standards, but large by just statistical standards. So you have a large variance here, you can see that. So this is a histogram where you have frequency on the y-axis and particle size on the x-axis, and I have a very wide variance, and that variance is collapsed. So I lose that variance through this process, and this process was entirely surface chemical. That means I actually modified the surface charge associated with these particles, and in that process the small particles started becoming larger, the large particles started becoming smaller, and ultimately all of them had the same size. So this was also modeled by using something called agent-based models. So this figures that you are seeing here, these cartoons, are basically from agent-based models, and these are real experimental figures, and you can see that a broad particle size distribution collapses to a narrow particle size distribution, and that seems to be coming out from our model, agent-based model, wherein what we are actually doing is basically assigning some features to each of the atoms and features to the surfaces. And these are kind of models that can be done in most undergraduate labs, because NetLogo, the agent-based software that we use, is actually freely available. So you can write those codes and play with those codes. So the algorithm we used was something like this. So I input the input radii, right? The sizes to begin with are not in my control. I input some empirical RA, RB, whatever, and then I compute the chemical potential associated with the A atom and the B atom, where A atom could be something like zinc and B atom could be something like oxygen, and I put it through this loop, this self-consistent loop, until my radii basically converge. So what did I find? I found that the chemical potential as a function of the radius of the particle, when I have charges on the surface, follows a curve like this. That means I could start here at slightly larger radius and the particle would actually shrink. Sorry, I could start somewhere here at smaller radius and the particle would increase in size but reach at this point and stop. I could start at a larger radius and the particle would basically converge on this size, right? And how do I write these equations? All I need are the hardness values for the atoms. So I need the ionization energy, the electron affinity associated with the atoms involved, and I would be able to run these equations. And the charge on the surfaces are actually considered a parameter to be varied. So you can identify the regime wherein you can see this size focusing. Again, as I said, these size focusing experiments were all low temperature, very easy to do. And we also found that there is a variation between R star and negative logarithm of dC naught, where D is the diffusion coefficient of a given atom in the solution, in the dispersion medium. C naught is the solubility product of the material. For example, zinc oxide, if it is made in ethanol, it is a solubility product of zinc oxide in ethanol. D would be the diffusion coefficient of zinc or oxygen in ethanol. R star would be the conversion radius. So as I play with the D and C naught, you see that R star becomes engineerable. I will be able to play with it. I can vary it. And this was captured in simulations, computer simulations, wherein we showed that small particles sometimes were having this growth events, and large particles were sometimes having shrinking events, and finally all of them were having the same size. Very robust, and we use something called hard soft acid based reactions in order to do this. We also look at ceramic sintering. For example, you could think about silicon carbide, zinc oxide, whatever, and you could put these particles together and you could compactify it. You could compact it by heating it up. What would happen at the neck really matters. You could have something like a phase separation happening in neck. That means to say, zinc oxide particles at the interface, something else could actually be forming. And based on, of course, the way you set up the computational model, you can actually predict this. This is an activity we have been doing, and we have been finding some very exciting results, especially concerning the physics of these extremely tiny particles, what happens at the interfaces, etc. So we use something called bond balance molecular dynamics for this, and this is now being used to study these classes of problems. So we are studying oxynitrides, morphology, phase transformations, defect energies, defect enthalpies, etc., etc. One of my dreams is to use this to even eventually simplify the study of ferroelectrics, which is today very challenging, especially if you want to predict as is whether or not there would be a deformation event that will give rise to ferroelectric behavior in a crystal. It's challenging. And to this effect, one of the students who is soon to submit his PhD thesis, he actually developed a very, very interesting set of relations, mathematical relationships that came off these simulations. But those relations seem to help us design ferroelectrics. I would be very interested in taking that work forward, in fact, because that allows very rapid prediction of ferroelectric materials, which is an extraordinary challenge today. Today, people still do lots and lots of experiments. You go to an average physics, chemistry, or engineering department that is looking at capacitors, they keep growing these ferroelectric materials with very little understanding of what would happen when you actually change the composition one way or the other. But this set of equations that Santosh Behera, who is soon to submit his PhD thesis, has developed actually provides a very quick passage into design through simple geometry and computation. So these are the ongoing activities in quantum dots, quantum nanostructures. We have also been looking at energy storage. So we have used quantum dots for supercapacitor applications in recent times. So we have a publication on that. That is a very interesting one. And others continue to take that work forward using quantum dots for supercapacitor applications. A big challenge, of course, is associated with the cyclability of these devices and so on. So prospect for collaborations and students. So I come from the materials department, but on campus, we also have interdisciplinary programs, thankfully. And as a consequence, students from different backgrounds can actually come into different types of departments. So they're all integrated in one way or the other. And this is a good model even for our universities, I feel. I mean, I know that administratively and bureaucratically, there are many, many barriers to interdisciplinary work in many of our places. But if we are even cognizant of it, we could actually move in this direction. Yeah. So we have everything from, by and large, iron and steel technology to processing to nanomaterials processing. And we have had a dental student, by the way, who graduated with the materials department. Tells you a little bit about the interdisciplinary nature of materials, people in general. So we have found that it can become a real melting pot where physicists, chemists, engineers, bio people, etc., come together, even medical doctors, etc., come together. So these are people I, by and large, interact with who are either in my department or neighboring or cognate departments with whom I have worked in one form or the other. I've just, or most importantly, who are my colleagues. So I am just enlisting their areas and expertise of work and so on. Also, for those of you who might be interested in energy, there is a solar hub here. So there is activity that involves solar fuels, and then solar fuels would mean generating fuels by using solar energy, then batteries, solar cells, and solar thermal, which is using sunlight for distillation and related purposes. Also energy storage in the form of heat, sensible heat it is called by mechanical engineers. Next is, the center's vision is to sort of have a very integrated platform where different types
Excuse me,
of
sir.
people.
Sorry to interrupt, sir. So, seems like some of the participants are saying that your PPT is not visible. Can you just?
Are you able to see now? 1 second. So I'll just stop sharing briefly. I'll start sharing again. Fine. So these are the domains of R&D in energy sector. So you're welcome to sort of explore options. And I'm sure that in your own Periyar University, there may be scholars in this area and so on. I am always open to having conversations, and I'm always very happy to brainstorm, create ideas and opportunities and so on. So, but by now I think you have a fair sense of what we do here. So, yeah, with this I stop. There are more things happening now, very exciting developments at the interface of machine learning, artificial intelligence, and materials design. And we have been publishing in that now in recent times. with focus on things like energy storage materials, semiconductor materials, etc. So we are developing new descriptors for them and testing it out experimentally whether or not it actually works. So it is very exciting because it actually brings the worlds of physics, chemistry, and engineering together. So with that, I stop and I'm happy to take questions. You're all welcome to engage with me now. Sorry if I went overboard with time. I think I lost track of time.
No problem at all, sir.
Yeah,
Not
yeah. But I'm available now for discussion. So I'll stop sharing, in fact, and hopefully you will all be able to see me and ask me questions. I'll turn my video on so that you get to see me.
Yes.
Yeah.
Thank you, sir. I would like to take this opportunity to thank you on behalf of the participants for this informative session. Thank you, sir, for taking time out of your busy schedule for us. Now, the session is open for questions. Participants with questions, please free to unmute your mic and ask your questions directly or else post your questions in the chat box or WhatsApp group.
Sure. What's the name of the moderator, the student who just spoke?
Rajeshri,
Sir
sir.
Rajesh,
Rajeshri. Oh, thank you, Rajeshri. Thanks for moderating this session. Yes.
thank you.
Yeah. So any questions are welcome. I mean, you can also ask questions that might in your mind be connected to your research and just throw it open for discussion. It's all right.
Yes, sir. So participants, you are free to unmute your mics and you can ask your question to the speaker directly. Yeah. Regarding the future of nanomaterials, particularly the carbon-based nanomaterials in energy storage devices, particularly CNTs, you have shown this single wall CNT also, single wall CNT and titanium oxide, right? So what's the future of these materials like graphene oxide, CNTs? Can they ever, I mean, whatever the reports that we have right now, can they better their efficiency, which is reported right now? Do we have a better future for this kind of carbon-based nanomaterial?
Yeah, I mean, carbon-based, yes, certainly. Because if you think about it, I mean, most of biology is carbon-based, you know, and a large amount of bio-waste, agricultural waste, etc., is carbon-based. So if you wanted to valorize it, if you wanted to attribute value to it, among the things you could do is carbonize it, generate value-added products out of it, etc. So definitely there is a lot of scope there. Also, from the more scientific standpoint, people have been exploring things like boron carbonitrides. New carbon chemistries are emerging, especially with boron involved. And another thing is, even in the world of supercapacitors, what I find stunning is that it is so hard to find something that is as good as something like graphene nanoflakes or something like even amorphous carbon, you know, for the purposes of use in a supercapacitor material for matrix, for choosing for making matrices that have perhaps other materials for supercapacitive action. But really, this is a very exciting class of materials. But you have to get into these with a lot of caution because so much has been done. I mean, the last 25 years, ever since IJIMA reported the presence of carbon nanotubes, there has been such extensive effort in this direction. So the way in which you ask research questions matters in areas like this. Like, what is it that you are solving matters. So you could be solving a problem that is still unsolved, and that will still be very interesting. So I would say, especially when you are entering into such a dense area like nanocarbons, exercise a lot of caution. Understand the recent most literature also very well. See what is the problem that is relatively unsolved, and then embark on that. Then you are probably going to still have a nice research program. So that would be my long answer to your rather short question. Yeah.
Okay, sir. Thank you, sir. That explanation is actually needed, sir. I mean, so And one question from the student point of view, sir. Those who are in their undergrads now, who want to pursue their higher studies in abroad, as you have very good exposure in that particular area. So, what should they do? How should they approach their degree or studies? You can say, how can they prepare themselves right now when they are doing their undergraduate? To get into research in future, particularly in premier institutes like IITs or somewhere abroad in good universities. So how should they prepare themselves?
Yeah, I mean, one thing that I learned over the course of my academic career here is that it really matters what you want to get out of life. So, for instance, you might be a very good and bright student, but you do not necessarily need to get into research also after BSc, because I find a large number of people who are talented in so many different things, because ours is a culture which is very monochromatic. We don't challenge students to go out of their comfort zones, or we don't challenge ourselves to go out of our comfort zones, and that is a problem. So what would be more interesting, I think, perhaps a better question is, how do I know what I'm good at? Okay, because after that everything else follows. It doesn't matter whether you go here, there, and if you are with good researchers, you will do good research. So what is necessary for all of you, especially undergrads, because you're very young, is not to get very caught up in tiny boxes. So that I'm studying this, I don't need to learn that, etc., etc. So don't limit your knowledge, don't limit your exposure and experience, because that, I think, is very, very helpful in having some degree of self-discovery. Like, what do you enjoy doing? That was a crucial question for me, actually. And it's not that and not only me, I think almost anybody who is in a relatively creative domain and who enjoys creative domains end up doing well only and only if you have that sort of a process built in. So the process really matters, and it could be anything. You could be a physics graduate becoming a business tycoon. It doesn't matter. Okay? And there is a lot of talent that is required for that. You could be a chemistry graduate who goes on to start a biotech company. It doesn't matter, and that would be extraordinary as well. So the step one is sort of realizing what your forte is, and it's very difficult. One way to do that is by putting yourself through a certain discipline, a certain rigor, a certain study routine, a certain project routine, a certain exploration routine, and not be shy, to sort of accept your own strengths and also accept your own limitations. But at the same time, work on your limitations. Especially when you're very young, you should work on your limitations. You should not be defined by your limitations. That is very necessary. So being active in projects, getting your hands dirty with research, all of that would be very helpful, because research, I've realized, is not a linear process. I mean, if you think about it, the kind of work that I was showing you, you cannot have a linear path to that. You will have to have a non-linear path. And students who come with a linear path anywhere in the world, they struggle, because you have to have the openness to learn on the fly. So yes. Long story short, I would say that, don't be too rigid with your approach. I mean, be very open, especially when you're young. Be open to experiments, open to people, open to disciplines, and not just young. It is good for people in general. It's good for people in general to just be very open to learning, not limit oneself, do projects, do it sincerely and honestly, be conceptually clear, ask good questions, explore, teach yourself, learn on your own, do projects as if they were as serious as your exams on a daily basis. That is one thing that actually helps, I think, in a big way. So I don't think you should get too caught up in the details beyond that, because after that, the world opens up for you. Okay, once you are clear about what you're looking for, the world opens up for you.
True, sir.
So, yeah.
Yes. Thank you, sir. And do we have any more questions from the audience? If you want to ask questions, you can directly ask the speaker. You can unmute your mics and you can straight away ask your questions, or you can post them in the WhatsApp group as well. Any more questions from the audience?
Yes, sir. Good afternoon, sir.
Good afternoon,
I am Dr. A. Nilufar, sir.
Dr. Nilofer. Good afternoon,
Yes, sir.
Dr. Nilofer. Good afternoon.
Good afternoon, sir.
Yes.
Sir, I have a question regarding the spectral studies, sir. What type of spectral studies specifically will tell the luminescence application, sir?
That's something called photoluminescence spectroscopy, madam. PL
Oh,
spectroscopy.
PL
That would
spectroscopy.
work. Okay, and then
Okay.
for any excitation that you use, you will have you will basically have the corresponding luminescence spectroscopy. For
Oh,
example, you could have electrical stimulus, then electroluminescence exists, then photoluminescence exists. And if there is luminescence, then photoluminescence study is a good starting point. So in all of these cases, it is photoluminescence. You're shining some low wavelength light and you're getting relatively larger wavelength light.
okay. Okay. Thank you, sir.
You're welcome.
Okay, any more questions from the audience?
It can be any question that was triggered by this talk. It need not even be directly related to the talk, but triggered by the talk. But triggered by the talk.
Anyway, you are involved in so many things. Just going through your profile, it took me a lot of time to even concise all these things to present it to the audience. So you have achieved so much in such a short time. I'm really amazed by the work that you have done towards research, as well as even in your other activities like building up the institution and outreach programs and all those things, which I could not detail in that intro that I gave. I was really amazed. All of us have the same time, 24 hours, but how some people like you are able to do so much in such a limited time. We are trying to find ways to make better use of our time, sir. That's the thing. So when people like you come in, when we interact with you, we get some idea, we get some guidance, and that's what we look forward to, and that's what I want my students in particular to get to know at this young age, so that they can do better when they come up. So thanks a lot, sir.
Yeah, I mean, I think we see when I was growing up, for example, there was this huge, in some sense, I do not know about many of you. The younger people may not even sort of relate to this experience, but maybe some of you would. There was this lack of emphasis on self-actualization. That is, oh, you're good at this, be better, be better. You're good at this, encouraging people to be good at what they are good at. Okay, so that was not there at all as a culture in our society. But what I've realized is that is all that is required. I mean, you could be here, there, anywhere, in any continent. In any continent, you could be here in this society and excel if you sort of are clear about what you have signed up for. With that comes a certain degree of excellence through attitude. The attitude actually becomes excellent, and hence the work becomes excellent. So that is, I think, foundational. So don't think of it as sort of a jigsaw puzzle to be solved, but you can think of it as sort of an evolutionary process where the puzzle itself is evolving and you enjoy the process. There's a lot of value to it. So, yes. But who is this? May I know your name, sir?
I'm Dr. Shankar Narayan.
Dr. Shankar Narayan, good afternoon. Yes.
Good afternoon.
Happy Pongal to you.
Yes. Oh, thank you, sir.
Yes. Yes.
Okay.
Where do you work, sir?
So in Sona College of Arts and Science.
Oh, in the same college. Wonderful.
Oh, yes, sir.
Which department are you in?
Chemistry, sir.
I see. So one of my first students was from chemistry background. So it was really enjoyable to work with him. And yes, he went on to do very well. And now he's in Bangalore. Okay. Like that, I've had, thankfully, because of relatively flexible system, and all of you can think about it. How do you make your systems flexible so that learning is facilitated? You might run into a student who is a non-chemistry student, but very good at chemistry. How do you encourage such a person, and so on? There's some value to that. Yeah.
Surely follow with your students, sir.
Sure. All the best. Thank you, sir. Thank you.
Okay, thank you.
All right.
Thank Thank you, sir, for being kind enough to clarify all our doubts with patience. As we are drawn to the end of the session, I would like to welcome Ms. Harini to give the vote of thanks.
Respected and our most distinguished guest speaker of the day, Dr. Tiju Thomas Sir, our beloved HOD Sir, Dr. Sridharan, Honorable Professors, and the participants present here. Good afternoon to all. I deem it a great honor to propose the vote of thanks to all who have helped us in making the webinar a fruitful one. First of all, I would like to thank our esteemed guest speaker, Dr. Tiju Thomas Sir, for making excellent presentation and enlightening us with his knowledge. It was really informative. Thank you so much, sir. I would also like to thank our principal, our HOD, our staff for organizing this wonderful session. Thank you to all the participants present here for paying your attention and learning. Once again, I thank all for your cordial cooperation. Thank you.
Okay.
To mark the end of the session, I would like to extend my gratitude to our honorable chief guest and each one of you. The feedback link has been posted in the WhatsApp group. The link has been activated for 1 hour. Participants are kindly requested to fill the feedback form within an hour, and your e-certificate will be provided within a week. Thank you, one and all. Thank you.
Thank you, sir. Thanks a lot, sir.
Thank you, sir. Thank you. Thank you to everybody. Bye-bye.